Now, with the z-distribution, we absolutely had to know what the population standard deviation is, because we need to know how many standard errors away from the mean a value is. We had to calculate the standard error, and for that we used the population standard deviation. In most instances of research, though, we do not know the population standard deviation. We only know the standard deviation of the sample set. So we can't use the normal z-distribution. Now we swap over to the t-distribution. Now, it is an equation that is very difficult. If you were to write this out, look at that equation. It's quite a bit more involved than the z-distribution. Fortunately, we have computer software that can do all of that for us. But it does introduce a new and interesting topic, and that is called degrees of freedom. Now, we haven't heard of that before. Now, the degrees of freedom, to work that out, is actually quite simple. It's just the total number of participants minus the number of groups there are. So if you were to do a trial or read a trial that compared the means of two groups, and there were 30 participants in each group, 30 plus 30 is 60, minus the two groups, minus 2 is 58. So that will be 58 degrees of freedom, and that gets built into this equation. It's actually very nice if you look at the different graphs here. Every one of the graphs there, that's all from a t-distribution, but they all have different degrees of freedom. So it's going to use that knowledge, how many groups you have in your analysis and how many participants are in that analysis, to draw a bit of a different graph. And you see the different kurtosis there. Some are more peaked with fatter tails, and that's how it goes. What we're trying to achieve here, and to very closely look like the z-distribution, the normal distribution, is to have very high degree of freedom, so have many participants in the study, to have large sample sizes. So we're going to introduce the t-test. We're going to look at how t-tests are constructed, but it really comes from this same principle as the z-distribution. We want to convert to standard errors away from the mean, and it's going to really depend on how big the sample sizes are, the degrees of freedom that we have. But we still want to know how many standard errors away from the mean we are. Now, most of the time, in our z-distribution example, we had everything on one side. Most of the time, we're going to have things on the other side, and we're going to have a deep discussion about this, a very important topic. But we're going to have so many standard errors away from the mean, would be 2.5% on the one side, 2.5% on the other side, combining them to be 5% of the area under the curve. And if we do it in this way, we're also going to duplicate our standard errors away from the mean. If we found 1.74, we'll also have a negative 1.74 on the other side, and combine those areas under the curve to give us a p-value.